All right, we'll now look at a set of problems which involve putting particles in a certain confined system. Okay, so we already know particle in a box type of things, but what happens when we put in, okay, very many, okay, so a large number of particles into a box, and that obviously involves the statistics of these things. So I'll not go into that much detail about the statistical physics of these quantities. Perhaps for the photons we may look at it a little bit, but we'll just now define our systems. Okay, so I'll just follow the notations in your textbook. Let's look at something that we are going to call solids. Okay, before okay, we put electrons, independent non-electrons, into something which we are going to call a solid. Let's just look at the single particle states. So suppose I have a system. Let's work in one dimension. So this is a topic which will be covered if you take a condensed matter course. Okay, so this is what we are doing is some very simplified electronic band theory. Okay, so suppose I have some periodic potential. Okay, so suppose I have something like this, and it goes all the way up to some length. So let me make this part dot dot dot. It's going to be some macroscopic length, okay, centimeters, millimeters, whatever, very long compared to electronic wavelength. But I have a periodic potential. Okay, so this is A, this is 2A, etc. Okay, until I get to n times A, which I'm going to call distance L. Okay, so n times A is equal to L. All right. What I will also assume is that I have periodic boundary conditions, which means that any particle that goes out here will enter over there. And okay, so a periodic potential which means I have V of x plus A is equal to V of x. So if I just move a distance A, I get the same potential. Okay, so I can work with obviously different types of potentials, but we'll look at a certain type of potential, which we'll call the Dirac potential. Okay, so this will assume that there's this. Okay, so you can think of these as the positive background of the atoms that you have inside the material. So you have a bunch of delta functions. So let me call this alpha delta of x. So this is minus alpha delta x minus A, and so on. So I have a periodic potential. Now I put my particle into this potential, and because of this structure of the potential, I expect to find the same sort of results from a wave function. Okay, so let me just try to show this schematically. Obviously, I cannot be very accurate, but A0, 2A, okay, 3A, and so on. So whatever physical property that I can measure here, I should be able to, okay, measure the same thing over there. So whatever, because of the periodic structure, at least that's the type of solutions that I am interested in. Okay, so I am interested in solutions which are going to give me the same physical properties as I go along this structure. So this is like a crystal, okay? And inside this crystal, I am looking at solutions. So what I mean is, if I look at psi x plus a magnitude squared, I expect that to be the same as psi x squared, okay? But it doesn't mean that the psi's themselves have to be equal. So psi of x plus a is going to be e to the I some big K times a, okay, some phase times psi of x. Okay, so each time I move, I develop a phase, okay, but obviously this satisfies that, okay. Now, since I have this periodic structure, I know that if I just look at what psi of okay, x plus NA, so that's going to be psi of x plus L, that I want to be equal to psi of x again. Okay, so if I go n times towards the right, I'm back in the original position. Okay, that's what I mean by periodic boundary conditions. So that now means I am going to include that phase n times. So it's e to the I n times Ka times psi of x is equal to psi of x. So that means that this has to be equal to 1. Okay, and that means that I have that quantity n times k times a must be equal to n times 2 pi. Right? Okay, so and what is this n? N can be equal to 0, 1, 2, etc. It cannot be larger than n, because if you put a number here larger than n, then because of the periodic structure, you just repeat the same number, right? N plus 1, putting here, is the same as that. Okay, so n times a, remember, was L, so k is equal to n times 2 pi over L. Okay, so I have a very large number of possibilities for k. In fact, you can sort of see that in the limit this L becomes very large. Okay, so this n is going to start from 0 and go all the way up to capital N. Then this is just going to form a continuum. Okay, so it's very small bits of L, 2 pi over L, just being added up. Okay, so that is the structure. Now, I want to find solutions to the Schrodinger equation with a certain energy. Okay, so this is my V of x. Now, I don't want bound state solutions. I could look at that also. But what I'm interested in is the case when the particle has some energy E. Okay, so what are the solutions to this energy, okay, when I have a potential like this? All right, so let's try to solve the problem. Okay, we know everything that we need to solve a problem of this type, given, okay, these conditions. Okay, I have certain conditions here that I have to also use. Okay, so what is the equation that I need to solve? Okay, it's actually quite easy. Minus h bar squared over 2m d squared dx squared psi is equal to, okay, but there's also this potential v of x, okay, psi is equal to e psi. Okay, by the way, this potential is called the Dirac comb, because somehow it looks like a comb. Okay, so I have something like this. Okay, so in between the delta functions, I have just v equal to 0. Okay, and because v is equal to 0, I have this simple differential equation d squared dx squared psi is equal to minus 2m e over h bar squared psi. And solutions are easy. Okay, so psi is going to be a linear combination of cosine kx and sine kx, right? So it's k equal to square root of 2me over h bar squared. So that's very simple. Now the problem is there are a whole bunch of boundary conditions that I have to satisfy. Okay, so let's look at what I need to satisfy. So this is my x, and these are my intervals, 0 to a, okay, to 2a, and so on. Okay, so over here I have minus a, which is the same thing as going around. Okay, so the wave function here is some psi of x, which I'll take as this. Okay, so I'll take this as a sine kx plus b cosine kx, right? So that's going to be my solution here. Now, my solution in this region, okay, is going to be psi of x, and I'll just use this expression. Okay, psi of, okay, I have to be careful. Okay, so what I have here is what psi of x plus a, right? So psi of x plus a, and if I want to use this expression, then I'm going to get something like e to the minus ika. Right? Please check my algebra. This is capital K, and what's going here is small k. So we'll be careful. Yes?
Why did we add a phase difference to the wave function? Does it come directly from the solution, or we assume that there should be a...
Well, the phase difference comes in from the fact that we expect solutions of this type.
Why do we know that this phase difference is increasing linearly with the distance period?
Because this must repeat itself, okay, at each interval. So I must have the same relationship between here and there, and there and there, and there and there, and at the end, when I come to the nth one, I should really get this thing n times repeated, should give me 1.
in order to just have a general expression for wave function.
Yes. Okay. Okay, so the psi of x in this region is what I have at psi at x plus a, which is this, times that. Okay, so it's going to be e to the minus I capital K a, okay, a sine k x plus a plus b cosine k x plus a. Okay, so this is just two of these regions. But what I need to do is I have to match them at this boundary. And if I can match them at that boundary, it will be matched automatically on all boundaries, okay, because it's just periodic. Okay, so now let's just go ahead with this. Okay, so what I want to do is I want the wave function at psi 0 minus to be equal to psi 0 plus. Okay, that's one boundary condition. But I also need the boundary condition across this delta function. Now, that is something we saw earlier, okay, but in case you don't remember it, I don't remember it. So let's just do it over here very quickly. Minus h bar squared over 2m d squared dx squared psi minus alpha delta x, okay, the delta function at the origin, times psi is equal to e psi. And remember what we did? We just integrated this, okay, from minus epsilon to plus epsilon. Okay, so we got minus h bar squared over 2m. Okay, change in the derivative from x to minus x. So it's going to be psi prime at 0 plus minus psi prime at 0 minus. Okay, that's just the integral of this second derivative. And then I have minus alpha times psi at 0 is equal to 0. Okay, so that's what we are after. Okay, so what the second boundary condition is psi prime at 0 minus, 0 plus, minus psi prime at 0 minus is going to be equal to, okay, there's a sign problem, but I think we'll, okay, so I move this on this side, it will be plus or minus, right? Minus alpha h bar squared over 2m. Please check my algebra. Psi 0. Okay, so move one to the other side, I get the minus sign. Okay, so these are the boundary conditions that need to be satisfied. So let's write them down. Okay, so the first condition, I take the 0 minus solution for that. So that's going to give me e to the minus I k a, okay, and multiplied by a sine k a, right, at x equal to 0, plus b cosine k a is equal to psi at 0 plus, which is just going to be b, and that's it, right? And I put x equal to 0, that's what I get. Okay? That's that equation. let's look at the second equation, which is going to be more of an algebra. So I need your help. Psi prime at 0 plus. So I differentiate this. All terms are going to give me a k. Okay, so I'm going to get a sine, well, sine becomes a cosine kx. Okay, so it's only just a, right? Minus b sine x, well, that's it. Right? Yes. Just ka. Minus the 0 minus stuff, so it's e to the minus ka. Okay, so this is also going to give me a lot of k's, so let me factor that k out also. Sine will give me cosine, so it's going to be a cosine ka minus b sine ka. The difference is going to be equal to minus alpha h bar squared over 2m. So this is the potential term, psi at 0. So the easiest one to choose psi at 0 is this one, because it's just b. Right, this is just psi at 0. I could have chosen the other one, but I just set them equal to one another anyway.
I think the coefficient will be 12 alpha over h bar squared.
Okay, let's see. Yes, you're right. Okay, thank you. All right, so now we have this equation, you see, which says, I have these terms here. Terms either have coefficients a or b, and a or b in the second equation also. So one trivial thing that you can immediately see, one solution is a is equal to b equal to 0, right? If I set everything equal to 0, it just says, but it's not an interesting one. So if I want something that's finite out of these things, I have to solve an eigenvalue equation, right? So this equation looks something like this, okay? So there are certain numbers like this, and then I have a, b. Everything is proportional to either a or b, okay? And one solution is put a and b equal to 0, then everything is satisfied. But if I want some finite results for this, I need to really solve an eigenvalue equation, so that I want to set things so that eigenvalues of these things are 0, and this becomes an eigenvector. Okay, so what that means is I have to adjust this k or capital K, okay, depending on what I have. Based on those things, I have to find out the solution. Okay, in any case, that's just the logic, but what I want to do, the way I want to do it, is I'm going to collect terms which are proportional to a on the left-hand side. So I'm going to get a sine ka, okay, from the first equation, is equal to, let me multiply by this factor, e to the I k a, that's just 1, right? Check my algebra, minus cosine ka times b. Okay? I've just moved this e to the ika to the right-hand side, and then subtracted this cosine ka from the right-hand side. So that's the first equation. Okay. The second equation, what I'm going to do is I'm going to first let me divide through by this k, okay, and put a 1 over k here, so that I don't have that. So similarly, I'm going to keep all terms that have an a on the left-hand side, a, so that's going to be 1 minus e to the minus ka cosine ka. Okay, that's that term is equal to b times sine ka minus 2m alpha over k h bar squared b. Oops, too many b's. Okay.
There is also exponential term.
Oh yes, sorry, what happened to my exponential? That's that, and there's one, yes. So there's an e to the minus ka, right? Over here.
Hocam aren't they e to the I K A?
Yes, ika. Thank you. You'll eventually get it right as a committee work. Okay, any more mistakes?
May I ask something?
Sure.
While we write the first psi function for the function before 0,
Yes.
why didn't we write x minus a times e to the power of minus a, I K A?
E to the
Why
what?
did we use minus a?
Okay, we are just using this equation.
Yes, but
Okay.
exponential has a minus in front, but not the psi function.
Why should the sine function have a minus? So what we are doing is we are using psi of x is equal to e to the minus I k a psi of x plus a, right? This is what this says. So I have e to the minus I k a and then x plus a. Okay, so now what we'll do is we'll divide these two equations. So first thing you can see is that these a's and b's will cancel, so we get this equation that we need to satisfy. Okay, so this thing divided by that thing is equal to this thing divided by that thing. So what I'll do is now I'm going to cross multiply these things. So I'll get sine ka, okay, multiplying e to the minus I ka sine ka minus 2m alpha over k h bar squared is equal to 1 minus e to the minus I ka cosine ka. Okay, and e to the I ka minus cosine ka. All right.
There is also a minus sign in front of e to the minus ik sine ka.
Where?
Right there.
This one? E to the minus ika sine ka. It's this one, right? Why do I need a minus sign? Where? It's this times that, right?
No, in the equation above, there is minus, minus, and we put it to the right side. It comes
Where? This is minus.
down below.
Okay, over here, I have a plus b sine ka. Okay, thank you. So that should be, okay, so let me move this b a little bit to the left. So it's minus. Is that okay now? Okay, so that means now I have a minus, where, over here. Okay, any other mistakes? Okay, let's go on. I have then minus e to the minus I ka sine squared ka minus 2m alpha or k h bar squared times sine ka. So let's expand that. It's e to the I k a minus cosine ka, and then minus cosine ka again, product of these two, and minus e to the minus I ka, no, plus cosine squared ka. All right, so we are almost there. So first of all, notice that there is a e to the minus ika times sine squared and e to the minus ika times cosine squared, right? So I can collect them together. Okay, so let me put them on the right-hand side. Okay, so I'm going to get, let's see. Let me, well, I don't know what I want to do, but let's do it this way. So minus e to the minus I ka, okay, sine squared ka. But there's another one on the other side, so it's going to be cosine squared ka. Very nice, that's going to be 1, right? And then I have this e to the minus ika plus ika, so it's going to be e to the minus e to the plus ika. Let me move the other stuff towards the right-hand side. So it will be is equal to 2m alpha or k h bar squared sine ka, okay, minus twice cosine ka. All right. Pass this around before I forget. Thank you. All right. So this is just going to be 1. And the left-hand side is just minus twice cosine capital Ka is equal to this whole right-hand side, 2m alpha or k h bar squared sine ka minus 2 cosine ka. So this is effectively the final result. Let me also cancel the 2, so that's, in fact, let me divide both sides by minus 2. So I get cosine ka is equal to m alpha over k h bar squared sine ka. Okay, so this minus, so let me change the order. cosine Ka minus m alpha k h bar squared sine Ka. Okay, so that means, remember the energy is hidden inside K, right? So K is equal to square root of 2me or h bar. Okay, so now I need to adjust this K so that I find a solution to the problem. What do I mean by finding a solution? Remember this, what this capital K was, wherever that was. Okay, so the capital K is equal to one of these things. So K is equal to n 2 pi or L. So L is some nice large macroscopic number, 1 millimeter, okay, 1 centimeter, whatever. So quantum mechanically, this is an extremely small quantity. Okay, but I have this n, which then varies that. So it's almost like a continuum. And whatever k that I put in here, I can adjust my n to find the corresponding k. Okay? So for each k, I can find this capital K. But I have to be really careful. This is not really a perfect continuum. It's just something close to continuum, right? So how do I go about this? Well, I have this function, which is a function of Ka. Okay, so it is, there's also a K over here. So it is something that is changing. Okay, so as a function of K, I have this function which is doing something. Okay, so you see, remember this, as K goes to 0, this goes to a certain limit, and then there's this cosine. So it's an oscillatory function. The effect of this is going to get less and less, so I'll remain with that. But initially, this can be quite large because there's this 1 over K, and I can have some oscillation, but then it will just oscillate going on with cosine Ka. So this thing is equal to cosine Ka, from which I have to find out what capital K is. But this may, initially at least, be quite large and be, okay, larger than plus or minus 1. So in order to find a solution to this, the magnitude of the right-hand side must be less than or equal to 1. Otherwise, there's no way I can find an arc cosine with a real K, right? So solutions only if this cosine Ka minus m alpha, obviously it depends on the details of the potential, k h bar squared sine Ka is less than or equal to 1. Okay, so in this region where the function itself is less than 1, so over here to over there, I have solutions. Okay, so if it's greater than 1, okay, so let me just do something like this so that it starts with a possible solution. So in this region, I have solutions. Okay, I can find various values of K. In this region where, again, the magnitude of the function is less than 1, I can find solutions. I can, in this region, find solutions, okay, and so on. So as it goes on, it's higher and higher K, it becomes easier and easier to find solutions because eventually this oscillates like cosine Ka and it's always less than 1. But in any case, for each one of these K values, I can now go back and find the arc cosine and find what capital Ka is. So that is going to give me possible energy. So that is going to end up in something like this. Okay, so let me just look at this instead of the k-axis. Let me look at possible energy levels. So I'll put the energy over here, which is going to be h bar squared, k squared over 2m. So this is 0. And somewhere over here, for certain values of k, I am going to be able to find solutions. Okay? And it's almost going to be like continuum. And then there will be a region where there are no solutions. So it's not possible to find a solution to the Schrodinger equation in a certain range of energies. Okay, but then I find energies, then again, there's a gap, and again, a bunch of energy levels, okay? And so on, okay? So after a certain energy value, I'm going to have lots of energy values, okay? So these things now form these almost continuum, what are things known as energy bands. And in between, you have these regions which are energy gaps. Okay, so in these materials, in this material, not all, you will not be able to have electrons moving in with any energy that you like, okay? They are not going to propagate. Over here, the solutions, if you force an arc cosine, you are going to get an imaginary k, which means you are going to get decaying exponential. So that means the electron will not be able to move. To get real values, you have to be outside these energy gaps. Now, inside these energy bands, you start from a point here, from an extreme point, which corresponds to cosine Ka equals 1. Okay, so that's one value of K. Then the next solution is for this small n, which I erased. Okay, so remember that this K is 2 pi over Ln. So in order to get a 1 here at the extreme limit, you are going to get n equal to 0. Then the next solution is going to be n equal to 1. So this is perhaps n equal to 0. The next one is n equal to 1. Okay, the next one is n equal to 2. Okay, until you get to small n equal to n. So each band will actually have capital N number of energy levels. Okay? So capital N is something large. Okay, we are talking about a millimeter size object, so 10 to the 23 cube root 10 to the 7 or something. Okay, so in 1 dimension, in 3 dimensions, 10 to the 23. Okay, the number of wells, potential wells that you have, it's thermodynamically large. So it's practically a continuum, but on the other hand, you have large number of particles. You also have 10 to the 23 particles, right? So it's not like you have an infinite resource there. You don't have an infinite number of places that you can fill. Okay, so this is the single particle energies. Now suppose I start putting in electrons in here. I start putting in, okay, certain number of electrons starting with the lowest energy levels. So I start filling them up. Now, since each band has n, okay, spaces for particles, and particles, if they are electrons, they can share each energy level, one with an upspin and one with a downspin. If I have n electrons, it will help fill a band. Okay, so n electrons corresponds to a half-filled band. If I have 2n electrons, then this band is all filled up. The next electron that has to go in has to go into the next energy level, which is above the gap. Okay? So you have all of these discussions about, for example, in an insulator, you will have all of these, okay, perhaps this one also, levels filled, and there's no space for the electrons to move. Okay, because for any electron to move, it has to really jump this energy barrier. Okay? But on the other hand, if it's only half full, something like this, in order to move, the electron can just go to the next higher energy level, which is very close to its present energy, and you have conduction. Okay, so a conductor is something which has unfilled band so that the electrons can move around easily. Okay, so this is a very crude discussion of band theory. Okay, obviously, if you take a condensed matter course, you'll do this in 3 dimensions with proper potentials and everything, and you get these structures which are very easily measurable experimentally so that you can connect with applications. Okay, I'll stop here. Yes?
For the socialistic function, don't we have a number less than -1 and k equals 0 because of the seat limit?
No, because this is 1, right? So near k equal to 0, this goes to 1 minus, okay, m alpha or h bar squared times a, right? So it depends on how big your interaction is. Okay. Okay, so I'll see you, I don't know when.